Even though we may not think much of it while we drink our own water in the United States, arsenic contamination of water is a global issue. Especially in certain countries in Asia, including Bangladesh, many drinking water sources do not meet the World Health Organization's limit of 10 micrograms arsenic per liter. Fortunately, there is technology designed to treat contaminated water such as electrocoagulation arsenic removal, also called ECAR. ECAR is a process where iron is precipitated and adsorbs arsenic, forming iron-arsenic solids that can be removed physically from the water. But if we really want to live out the magic word of sustainability, we have to realize that the life cycle of that arsenic doesn't end there. For example, how is the ECAR waste disposed of, and how well does the arsenic stay contained in that solid form? Because engineered landfills may not be available, one method that is recommended is to mix that ECAR waste with cow dung and dispose of the mixture in the environment. This method is based on evidence that arsenic methylators in the microbial communities provided from the cow dung and enriched by the surrounding anaerobic environment will transform the solid arsenic phase to a gaseous arsenic phase. But before we go any further, let's explain what an arsenic methylator is. So the clump of little sticks here are members of the genus Methanosata, a group of archaea known for their ability to perform methanogenesis, the biological process of producing methane. However, some of the enzymes used to produce methane also allow for the attachment of methyl groups to arsenic, a process called arsenic methylation, and these byproducts are easily volatilized and can escape to the atmosphere. Sounds useful, right? If dilution is the solution to pollution, then releasing these amounts of arsenic to the large expanse of the atmosphere is perfect. But of course, there's always questions and complications. To what extent does this process actually happen? Many studies in the literature say that very little of supplied arsenic is actually volatilized, and it seems any study that says that a substantial amount is released doesn't provide a sufficient mass balance, so we don't even know if it's true or not. And even if it was a substantial amount, the arsenic that we're concerned with is contained in a complex of iron solids. How available is that arsenic to the microorganisms that work with it? To answer those questions, we created our own reactors to see for ourselves. Each reactor contained ECAR waste, anaerobic digester sludge, and cow dung to ensure the right microbial consortium was present. As gases in the reactor built up over time, we collected them with a syringe, but as the gases were collected in the syringe, they also passed through a silver nitrate silica bead matrix that captured any arsenic gases and allowed the passage of any other gas. The other gases could be quantified using gas chromatography, mainly methane and carbon dioxide. After around 17.5 days, the reactors were shut down, the contents were centrifuged, and the liquid and solid phases processed and quantified for any arsenic using the inductively coupled plasma mass spectrometer, ICP-MS, which is a machine that allows us to quantify low concentrations of various metals. This way, we were able to keep a mass balance and account for almost all the arsenic starting up as ECAR waste in our system. Through this, we verified that less than 0.02% of the arsenic in the system was volatilized, which is consistent with the literature, and around 5% of the arsenic was mobilized in the liquid phase. The rest of the arsenic remains in the solid phase. Also, using different inhibitors of methanogenesis, we were able to see that observable methanogenesis correlated with observable arsenic methylation. However, now that we have this mass balance and we know where the arsenic goes, we can see that the cow dung arsenic volatilization method with its current recommendations is not an effective disposal method of arsenic dilution into the atmosphere. Instead, other methods like stabilization in concrete has shown to allow very little arsenic leaching comparatively. But this leaves other questions. What microbial processes are responsible for the mobilization of arsenic from reduced iron waste? Arsenic reductase? Arsenic oxidase? Right now, we're in the process of analyzing the genetic composition of the microbial communities and the expression of these genes by extracting DNA and RNA from the reactor's biomass and quantifying the number of genes with quantitative polymerase chain reaction, or qPCR. Above all, what did I learn? Understanding how to really engineer technologies to accomplish water sustainability is difficult but necessary. In a world continually trying to grasp the concept of sustainability, it's going to take a lot of science and engineering to help us reach that goal, but we can see it happening one question at a time. I would like to thank my graduate student advisor Tara Clancy, my faculty advisors Professor Raskin and Kim Hayes, as well as the SURE program for the opportunity this summer to understand more of what environmental biotechnology can do for the future of sustainability.